Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to learn about halogenation reactions on the alpha carbon. Okay, so we have a few things to learn about for here: acid, base conditions, haloform, and the HVZ, Hels-Volhard-Zielinski reaction. Those are the four we're going to learn about right now. So this is going to start the beginning of the rest of the chapter, which is all about just reactions. So we're going to start by halogen, we're going to move our way into alkyl groups, then we're going to do things known as acetoacetic synthesis and malonic ester synthesis and a whole bunch of other similar concepts. Okay, but section 4, halogenation. So let's get started. So the first thing is acid conditions. Now remember what I said earlier in the previous video. I said that acid things happen one time, right? So only one time halogenation occurs. Okay, halogenation occurs. Okay, so this is under acid conditions. So for example, if I have, and by the way, the halogen itself could be Br2, Cl2, I2. It really doesn't matter. So any halogen will do. And we don't have to worry about like which one's more likely to do it over another. This isn't really about, we're not going to concern ourselves with that type of consideration, right? But we have some sort of halogen, any halogen, so Br2, Cl2, I2. F doesn't usually do anything at all. I'll put it in here, but usually halogen, like fluorine, is just, it doesn't really do much. But we'll put it in here regardless. So what's going to happen is we have some sort of halogen, right? But we have it in an acid environment. So it might be, let's just write H3O plus or H plus, and it's in, let's say, Br2. So what's going to happen is we're going to protonate the oxygen. Remember the acid template, make it positive. And now we have to go, anytime you do acid, you have to show an enol, right? You must go into the enol form. So what I'm going to do is I'm going to have the conjugate base, let's say if this is H3O, let's say it's water, it's going to pull off the H. We're going to go into its resonance form like that, and you get to the enol, okay? So after you pull off the H, you do a delocalization and you get to an enol. Now you have to show the enol, right? This is the enol. Once the enol is formed and it tries to go back around, this is when the Br comes in. Remember, we're looking for a positive source. So the Br of Br2 is the positive source. So the Br gets pulled in while the other Br leaves. And we wind up making a connection on the alpha position. And we get this right here, positive. Okay, and you get to that, and then finally you have some kind of deprotonation. So it could be water, it could be Br. I could just write minus H plus, meaning I don't care. Some base pulls it off, whoever it is, who cares, and we're good to go. You could do that on your test. You don't have to show exactly who pulled it off. It could be the Br that pulls it off or the water. But you see the point? This is the product right here. This is it. So you have a monohalogenated product. Okay, only one time halogen comes in. All right, so now what's H plus? Well, it could be H2SO4, it could be H3O, it could be HX, like HBr, right? So H plus could be any of your normal things that you know that I've always given you a list of for the past few chapters, like H2SO4, H3O plus, it could be HX, okay? It could be NH4Cl. Remember that one? We learned about that in the chapter 17, acyl halide becoming an amide. So all these different acid types, don't get too caught up on what the acid is. Just realize the general flow. And what's really important to note, and you'll see why I keep emphasizing this, is that you have to show the enol in acid conditions. In base conditions, you really don't have to show the enol, not for the mechanism, but in acid you do. Okay? And we're going to see that now when we go over the base right now. Okay, so that's the acid pathway. Let's talk about the base pathway. Now, for the base pathway, this is special. It happens many times. Let me write polyhalogenation. Polyhalogenation occurs. Now, remember, you have to first figure out where's the acidic position. And for our templates, it's always alpha. But we talked about from section 1 and 2 videos that if you have, like, let's say a double bond here and then a carbon, well, and this is an aldehyde, for example, well, then this is where we're going to pull the H from, right? So you always have to recognize that it's really about allylic position. I don't want you to forget that. But for our templates, we're always doing it simple. So we're going to start like that. Now, let me just put it like this so it's symmetrical. I don't want to worry about which one happens first or second. We'll talk about that soon. But what I do want to emphasize is that each alpha carbon here has 2 H's on it, right? So let's keep that in mind. So if I have hydroxide and I have halogen, let's say Br2. And once again, it could be any halogen, right? So Br2, Cl2, I2, F2, doesn't matter. Okay, so now, again, fluorine tends to be the least likely of all of them. It's usually Br and Cl that we deal with, but it could be any of them. So it's not really restricted at all. All right, so here we are, and what we're going to do is we're going to pull off a proton, as we know, and we're going to make this negative. And again, we're just assuming to ignore the fact that we also go through the hydrate, right? Remember chapter 16? We just ignore that for now. So in addition to hydrate, we know we make alpha anions. And now, normally when the alpha anion forms, we have to show the enolate, right? So we would go ahead and draw the resonance. But we don't have to do this, not if we're doing mechanism. So up until now, I consistently showed you over and over again, and I'm going to go back to it, that when you do these mechanisms, on the base, I showed you the enol, the alpha anion becoming an enolate, and then the enolate getting protonated. But remember what happens? We say that the enolate goes back down and becomes alpha anion, and then something comes into it, halogen, right? So remember this simplified version? You pull off the H, you put in the halogen. That's all I'm going to do right now. Okay, so this one here, actually, I didn't show you the simple version, but I did it just now. In this section here, right? So simple version, it's actually not that simple. You have to go to enol and then you reverse back out and put the halogen in. So let's go ahead and look at the base. So I pulled off the H. I know I have resonance. I know I make enolates. I know I make enols, but I don't care. What I care about is this right here, negative, and then Br gets attacked. So you pull in the Br and the other Br leaves. So now I have a Br added on. Now this is going to happen over and over again. However, I want to show you, this is important, the next one to lose a proton. See, right now it's symmetrical. They're both ethyls. So I happen to pull from here. It's the same as there, right? But what's important to note is that once you put a halogen on, then this carbon here is now even more positive than it was before. So this carbon alpha is positive because of the carbonyl, right? And that's why there's acidity here. And it has resonance stabilization after it loses its proton, right? But what happens when you put a halogen? It gets more positive. So this is more acidic now than the left side. So this is more acidic than it was before. And so that means that now if this was able to, hydroxide was able to pull off an H from here, well, it's definitely going to be able to pull off another H from there because now it's even more acidic. So once you put a halogen in, you have to work that side completely before you go to the other side. So that's the point. So now this is negative, and then you put a Br in. Okay, so Br gets attached on again. So now we have a dibromo ketone, right? And this is going to happen over and over again. So from here, I just wanted to show you that point where you pull the next H from, but this is going to happen again and again, and eventually you're going to get to the point where you pull off as many H's as you can, and you get Brs taking all of its places. So you can't stop this from happening. So it's almost like once you kick this in gear, every time you put a Br on, it becomes even more acidic, the molecule. So unlike acid pathway, it's very hard to even get one H to get pulled off because you already have acid around, which is much more acidic than the carbon. So it's really difficult to get even one to happen, right? Usually you have to raise the temperature, you have to do some pressure changes. You got to do things in order to get this to happen. So if it does happen, it happens once and it never happens again. Okay? That's it. But in this case, with base, since you were able to pull the first H off, it might take a long time, but once you do that and you get a Br in there, now this is acidic. And it keeps lowering the pKa every time a Br comes in. it makes it more and more acidic. Okay, and that's why it just keeps happening over and over again. And there you have it. So that's the base condition. Now the next reaction is very similar to this. However, it's a very special case. It's called the haloform reaction.